So if we have some substance, what was the definition of a substance? Back a while back ago, but a substance, how was it defined? That's back in chapter 1. That's the definition of substance, right? It was defined very specifically back then, but a lot of people use it loosely. So sometimes people put pure, although it's not necessary to put pure here, based on the definition. But since people don't use it as precisely defined, then some people will use the word pure. Kind of makes sense. Pure substance. Pure substance would be what? An element or a compound. It's an element or a compound. And so, like lemonade wouldn't be considered a substance. It'd be considered what? A mixture. So we have even pure lemonade. Well, is there such thing as pure lemonade? Not really, because you could have different concentrations and composition could differ, and so there's not really. Whereas water itself, or the components that it's made of, would be pure substance. Well, for pure substances, we want to know the properties. So what kind of properties do we want to know? Well, there are two types of properties. What are they? The two types of properties: the physical properties and the chemical properties, right? And so we want to know the physical and chemical properties. Well, you used to have to buy kind of an expensive book to get the properties of, like, name of a book that you might be able to find physical properties compiled in. I think I gave 2 of them. I don't know if anybody recalls.
About a really big book.
Really thick book, yeah.
Showed a picture of it.
Showed a picture from Amazon, right?
Yeah.
It's like a couple of $100 or something. Anybody remember the name of that book? No. 2 of them actually I showed. One was called the CRC Handbook of Chemistry and Physics. The other was called the Merck Index. So this is just. It's always good to go back because it's easy to forget stuff. So it's always good to go back. And to go back is just to remind yourself. This is what they say advertising works, because advertising, people forget. They forget about going to eat wherever, and so they need reminders. So if you're continually reminding yourself, these types of things, it's a lot harder to forget. But anyway, we don't have to get the CRC. Wikipedia is a pretty good source for properties, I think. Wikipedia, I looked at the numbers, they're pretty reliable. These numbers here. In fact, if you look at this excerpt here, this looks like it was taken out of the CRC. So we look at the properties over here. First, the names, Sodium chloride, other names: common salt, halite. Halite is the mineral. So this also substance is just NaCl, rock salt, saline, sodium chloride, table salt, regular salt. Sea salt's a mixture. A whole bunch of numbers for referencing. Here are the properties. Well, one thing you notice about the properties, things like density, melting point, boiling point. Sodium chloride forms a lattice structure. Ice we didn't get a lot of the properties, just an idea of the properties. For example, sodium chloride is expected to have a high melting point because of its lattice type structure versus ice. Does ice have a high melting point? It doesn't. Ice is a molecular solid rather than a lattice type solid. So, what holds the molecules together versus what holds these atoms or ions together in the lattice are quite a bit different in terms of strength. But anyway, we can go down. It has a high melting point, a high boiling point. The melting point, if you've ever tried to melt sodium chloride, it melts at 801 degrees C, which is quite high. I mean, does your oven go that high? That would be 1474 Fahrenheit. Can you set your oven that high? No, it would melt. Your oven would melt probably at that high of a temperature. And so, how can you melt this stuff? Well, you can buy special ovens. I used to use a special oven. This oven that I used went up to 1600 degrees C, closer to 3000 Fahrenheit. That's a very special oven. That was an electric oven. Had a platinum heat element with that. It was a very expensive oven. Anyway, this is soluble in water. What do you notice about all these properties? All these properties are physical or chemical, or a mix of physical and chemical? All these properties are physical properties. There's no chemical properties there. So let's scroll down. The more physical properties, how the atoms are put together, the structure, some other things. That's the end. And so what are the chemical properties? Well, here's a chemical property. The chloralkali process. Sodium chloride and water yields chlorine, hydrogen, and sodium hydroxide. So is that it? Soda ash industry, the solvay process. Maybe let's take a look at that. Solvay process. The solvay process. Oh, here we go. Sodium chloride and calcium carbonate makes sodium carbonate and calcium chloride. Sodium chloride plus CO2 plus NH3 plus H2O yields sodium bicarbonate and ammonium chloride. That's it. So, one thing you'll notice when you look at the chemicals, even though Wikipedia is pretty good, it just takes some random sampling of chemical properties. That's it. This is really not as systematic. I mean, if you look at the physical properties, it's very systematic here. In fact, they have this template they use for this. But when you look at the chemical properties, it's just whatever somebody's interested in. Maybe they're interested in this, maybe they're interested in that. But it isn't really systematic, and that's a problem, because is that is that the way we learn chemical properties? We just learn from individual reactions. So, for example, you take sodium chloride or salt and you mix it. Okay, let's take some sodium chloride. We mix it with hydrochloric acid, see what happens. And then we mix it with hydrobromic acid, see what happens. Hydroiodic, what else? Hydrosulfuric acid, hydrocyanic acid. Let's get rid of all the hydros, and then we move on to sulfuric acid, nitric acid, perchloric acid, chloric acid, chlorous acid, hypochlorous acid. And then we move on to perbromic acid, bromic acid, bromous acid, hypobromous acid. And so, is that how we understand the chemical properties of sodium chloride? We just if we wanted a comprehensive list, we'd have to test sodium chloride with every known chemical. How many known chemicals are there? Millions upon millions, so we'd have to do a lot of reactions there. No, that's not the way we do chemical properties. So even though it seems like, wow, the physical properties are so well organized, the chemical properties are just some random sampling of chemical properties. It's not organized. And so this is why I'm trying to, and the books are like this. The books, not just the Chem 4 book, the Chem 1A. The Chem 1A, if you look at the Chem 4 book, it's random sampling. They give you like 4 reaction types to memorize. Those 4 reaction types are nowhere near comprehensive. A lot more reactions than that, right? And so it's just kind of a sampling. Okay, here's a sampling of chemical reactions that occur. But then you might go, well, it's just too horrendous of a task. I mean, if you're looking at so many different types of reagents. Reagents are chemicals. Another word for chemicals. You have so many different substances. Substance is another word for reagents. Substances, reagents, chemical reactions, all the same. It might be too overwhelming. Well, it's not too overwhelming, so I don't know why it's not organized like this. Although some people are going to automatically, and I've been doing this a long time, this method of organizing, and some people will not allow it to click for some reason. It's blocked, mentally blocked. But it's just a different organizational scheme, and the organizational scheme is not that complicated. All it takes is a little bit of commitment and memorization, and you'll be okay. And so, how many different types of chemical reactions are there? How many main types of chemical reactions are we going to deal with? If you Chem 4, it'd be, what would it be in Chem 4? Combination, decomposition, single replacement, double replacement. 4. Yeah, that's a pretty good sampling of chemical reactions. And it's better than this right here, But we're going to organize it differently. How many types of reactions are we going to look at in this class? The 4 that they say follow a certain pattern. There's going to be a pattern: A plus B. AB yields A plus B. That kind of pattern. But we're going to look at how many different types of chemical reactions? 3. And so if somebody were to, we'd have it organized here, as far as the chemical properties go, we have reaction type 1, reaction type 2, reaction type 3. That pretty much covers chemical reactions. Rather than just taking, if we had that way, then from there we can look at the combination, the decomposition, the single replacement, the double replacement, because those fall into certain categories. And so the physical, we typically can make predictions, physical properties, this comparison. Sodium chloride is expected to have a high melting point. What is it specifically? We can look it up there and measure it. The chemical properties, though, let's take a look at chemical properties. And so as far as chemical properties go, the first type of chemical property that we look at are the metathesis. Another way of thinking metathesis is what? Yeah, ions. What about ions? Switching ions, but it's a little bit more than switching ions. We could switch ions, but they might not connect. We can switch ions, just mentally switch the ions, but there has to be something that connects them. There has to be some sort of what we call driving force, right? There has to be some kind of something that draws the ions together. And so I called it something else, a little different. What did I call it? The ionic bond, or in other words, the ions have to be a favorable ion combination. So favorable ion combination, somebody mentioned, isn't sodium chloride a favorable ion combination? I mean, look at it, sodium chloride, salt, high melting point, high boiling point, so that ions are held together tightly. But I don't consider it a favorable ion combination. Why don't I consider sodium chloride a favorable ion combination? The reason I don't consider it is, if you have salt water, do the ions come together to form salt, or do they stay separate to form salt water? They stay separate. The only time the ions are going to come together is when they're forced together. How can you force the ions together? You have to evaporate all the water. It's like a fish, a pool of fishes. Eventually the pool gets smaller and smaller, and they're going to be forced to come together. Otherwise they kind of stay apart, the fishes would, right? And so the same thing, the sodium ions and the chloride ions kind of stay apart until they're forced together by, they're forced together by evaporating out all the water. So let's see, is this it? So let me show you what I mean by this. Have it up. How did I put it down? Let me see, where did I put it? Here. Okay, let's look at, this is a simulation based on theory. This would be, we'll call MD molecular dynamics. Molecular dynamics is just molecules in motion. Here, do you see these little green things? These green things are the electrical attractions holding the water molecules together. It's holding everything together. Water molecules are extremely light. They only weigh about 18 U. And so, gravity is not going to hold them in the liquid state. A small breeze can knock a bunch of these off unless they're held together tightly. These are held together tightly by these kind of electrical interactions here. You can see there's vibrational motion. Do you see that? Some rotational motion and some translational motion here. Now, when we look at the ions here, here's sodium ions and chloride ions. They aren't coming together. They might come close, but they don't get stuck together to form a precipitate. And so these stay dissolved in water. Of course, as the water evaporates, let's say you heat this up, you boil off the water, then the ions are going to be forced to come together, especially when there's no more water left. Otherwise, they stay kind of apart from each other. This has been slowed down. It's much faster. This would be more real-time here. Let's take a look at this. So that was the slow-mo version. Here's the molecular dynamics version here. This is a real-time kind of version here. And you can see the ions are apart here. Small ions here. That's different than something like this. If we look at something like let's see if I have AgCl. AgCl. Where the silver and the chloride actually like each other, we can see, I do have it. Let's see, where did I put that? Oh, here. This is it. This is both we call macroscopic and the particulate level.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond, and bind with other silver chloride molecules that have precipitated from solution to form the solid.
Yeah, we don't call them molecules. No, we call them units, formula units, whatever else, units. But you can see, this is different because, these are going to get stuck together. They're actually attracted to each other.
And bind with
Whereas the
when they
sodium ions and
encounter
chloride ions
silver
stay
ions,
apart.
gray and green respectively, are in solution.
So this is what I mean by favorable ion combinations. Silver ions really like chloride ions, so they're going to come together even, in these solutions. And if you speed the solution to real time, it's that crazy thing you were saying. That was like, but these are still going to come together and bond. And so what we're looking at is favorable ion combinations. So what we do is we take a look. And favorable ion combinations can come in a variety. But for metathesis, what we primarily look for are things that precipitate, like that. And that white solid that was forming is called a precipitation. I've seen that in lab last week, precipitation. But metathesis, we look at the ions. Sodium ion is one. What ions do sodium ions like? Well, then we go, think about the solubility rules. The solubility rules are group 1 and ammonium are all soluble. That means they stay away from other ions for as long as possible until all the water has been evaporated off. And then they'll finally come together, only when they're forced to come together. And so for metathesis, these are not reactive. And so it's like no reaction, not reactive. There's no real ions that they really like. However, chloride ions are a little different. We have chloride ions. Chloride ions do like certain ions. They like certain ions enough to come together to form a solid PBT. What are they? Chloride likes. Well, then we think back. Chlorides, bromides, and iodides are all soluble except for silver. So chloride likes silver ions, like in the video. Will come together with silver. But not just silver. What else will it come together with? Yeah. Lead, 2, and mercury, 1. And so if I had lead 2, the same thing would happen. If I had mercury 1, the same type of thing would happen. They'd come together, form a PPT. And so as far as metathesis properties go, sodium chloride will react with silver ions, lead ions, and mercury ions. Lead 2 and mercury 1. So we know there's going to be some metathesis chemistry there. Okay, then after metathesis, we go on to acid-base. Now I have to tell you this. Acid-base. I'm going to ignore a certain category of acid-base reactions because we don't have enough time to really talk about it. What we're looking at is Bronsted. And so, note, we are not considering Lewis acid-base. Skipping Lewis acid-base. And just looking at Bronsted. The reason is Lewis acid-base is more complicated. Quite a bit more complicated. So these are discussed in Chem 1B. So you have to realize that, acid-base, to do a proper acid-base evaluation, we look at both Bronsted and Lewis. Bronsted because it's a heck of a lot easier than Lewis. And so we look, actually we only have to look at Lewis because all acid-base reactions are Lewis acid-base reactions. But since Lewis is so complicated, we subdivide it. And we come up with a category called Bronsted, which is way easier. And so we're just looking at the Bronsted acid-base. And so what that means is we might miss the reaction, but that's okay. We might miss a Lewis, but we'll get the bulk of it. So we'll get a decent feeling for these. So how do we know what the Bronsted acid-base properties are? We just check the chart over here, and then we look. On the left we have the redox chart. On the right we have the acid-base chart. The acids are on the left here, the bases are on the right. The acids donate an H+, the bases accept it. So it's an H+ transfer between the acid and the base. Now, we look for sodium ion on the chart. Is sodium ion a good acid? Well, what's the best acid on this chart? the best acid on the chart is perchloric acid. So we look, is sodium ion a good acid? Is sodium ion even on the chart? No. Why? Because sodium ion is not a good H donor, because sodium doesn't have any H atoms attached to it, does it? No. Oh, maybe it's a base. Sodium ion a good base? And so we go down. What's the best base on this chart? Fluorine is good. You have that in your memory, but it's for the other chart. Fluorine's for the other chart. What's the best base on this chart? Methide. Good. Good. I asked this morning, nobody knew. So I'm glad. Nobody knew the name of this. It's good you remember. Methide. Methide's the name of that. It's the best base. But do you see sodium ion? It's the best base on this chart. What's the best base on that chart up there? Right. The best base on that chart on the right is NH2 minus. NH2 minus is called NH3 is called ammonia. NH2 minus is called amide. Good. Amide. There's a pattern to this. Do you see? What's this one called? Sulfide. You know, sulfide, amide, oxide, hydride, methide. Methide comes from methane. Hydride comes from hydrogen. Oxide comes from hydroxide. Amide comes from ammonia. Ammonia goes to amide. And so you can see there's definitely a pattern in the names. You know, and so it's useful to name these things so you can see nomenclature in action. But you look over here, do you see any sodium ions? No. So what we say is this. We say that sodium ions are neutral, unreactive. And so sodium ion is not reactive. Okay. Neutral. How about chloride? So sodium ions aren't going to do anything acid-base wise. They're neither acidic nor basic. That's what I mean by neutral, neither acidic nor basic. Neutral can mean different things, though, as we'll see when we talk about acids-bases later. Chloride ions I don't see on the acid side, but I do see chloride on the base side. So let's scroll up here. Do you see chloride? Chloride's a base. So, chloride's a base. So, but, okay, it's a base, but you have to be able to interpret it. Is it a strong base? No, it's a weak base. In fact, how weak of a base is it? Well, it's a pretty weak base. I mean, it's at what's the worst base on this? The best base is methide. The worst base is this one, Tom? Perchlorate. It's in the top 5 of the worst bases on this chart, right? And so that means it's a pretty bad, bad in the way that it's not a good base. In fact, this is something you should know. All these bases are so weak, they aren't even considered bases. In fact, you know, the conjugate relationship holds here. If you have a very strong acid, then the base is going to be very weak. And in fact, this is so weak, it's considered neutral. That is, it's not considered a base, but it is so weak. So weak, it is not considered. So let's say you spilled some acid, like maybe you have some battery acid spilled on the ground or on the floor. Could you sprinkle some table salt to neutralize the acid? Will that work? No, it's not going to work. I mean, sodium chloride isn't even considered a base. Even though it's on the base chart, it's not really considered a base. And then I said, if you run out of antacid, could you use table salt as a good substitute for antacid? No, it's not going to work because chloride, well, somebody might argue it will work. Hey, it's here. It's a base. It should work. It should neutralize acids. A base doesn't neutralize acids. It's a base. But the thing is we have to be able to interpret the chart here. Just because it's here, you know, we need to know a little bit about its reactivity. Likewise, the same thing goes with methane gas. You know, methane gas. Do you consider methane gas a pretty good acid? Methane gas is on the acid side here, just like hydrogen. You really consider hydrogen and methane an acid? Or even hydroxide? You know what people consider hydroxide? People consider hydroxide a strong base. They don't really consider an acid. That's because it's so weak. I mean, these acids are so weak that people don't really consider these acidic. So the same thing goes here. Yeah, it's a base, but you know, it's too weak. And so far, for acid base, sodium chloride is pretty unreactive. It's not really going to react with anything in terms of acid base reactivity. All right, but that's not all we look at. So we look at metathesis, we look at acid base, and we look at redox. For redox, what do we do? Well, we just consult this chart. This redox chart gives us a clue as to how things react. And so we just look for it. Two things you should know. F2 is what? The strongest oxidizer. It wants the electrons the most. It's the most electron poor out of all these species. And then at the opposite extreme, we have Li. Li is the strongest reducer. And then there's the conjugate relationship here too. So F2 is the strongest oxidizer. That means F minus must be the weakest. If F2 is the strongest oxidizer, it really wants electrons. Once it has those electrons, it doesn't let them go. So F minus must be the weakest reducer because it just doesn't lose the electrons. They're stuck on there. Well, let's try to find sodium ions here. We see sodium ions in the redox chart. And I do. I see sodium ions right there. So now when we look at redox, you see sodium ions are right here. And, sodium ions are what we call an oxidizer. So sodium ions are oxidizers. Are they strong oxidizers, moderate oxidizers, weak oxidizers? Strong oxidizers like fluorine? The strongest oxidizer is fluorine up here. So would you rank it with fluorine in that crowd? No. We'd rank it at the bottom, which means it's weak. How weak? How weak of an oxidizer is sodium? Like, for example, you know what you should do? If you use table salt on your French fries, you know, you better start popping, you know, antioxidant pills, you know, antioxidant supplements or whatever to tame that sodium ion, because the sodium ion is pretty good oxidizer. You don't want any oxidative damage to your tissue, do you?
No.
Do you worry about it? No, you don't worry about sodium ions oxidizing ability because it's so poor. I mean, this is one of the worst oxidizers around. In fact, it's probably so poor that we don't really consider it much of an oxidizer at all. And so, yeah, sodium ion's an oxidizer, but it's a very bad oxidizer. But so unreactive, it's not really considered. It is too weak to really be considered. It's too weak to be considered. Its conjugate, if sodium ion is too weak to be considered, then its conjugate must be so strong, right? And what is the conjugate of sodium ion? The conjugate of sodium ion is the reducer of sodium metal. So sodium metal must be an awfully powerful reducer. Carcolici has a term for this. He has Dr. Jekyll and Mr. Hyde, because both of these are the same element, sodium. But one is very reactive, the other is very mellow, very stable. And so which one is very reactive? Well, sodium metal is very reactive. And so is that Dr. Jekyll or is that Mr. Hyde? Mr. Hyde was the super reactive, volatile one. Okay, so this would be Mr. Hyde, and then this would be the mild-mannered, stable Dr. Jekyll, right? Did I show the video of sodium? I didn't show you the video of sodium metal? So what do you do if you have 50-gallon drums of Mr. Hyde or whatever? So here's a YouTube video of this. This is somebody, I don't know the original, somebody edited this. I wanted just the original one without this commentary. But the original one got deleted and this one replaced it, but anyway.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
I haven't seen this. Don't flush sodium down the toilet.
This is a solid chunk of sodium metal. This stuff is number 11 on the periodic table of elements, and it is extremely reactive when it comes in contact with water. So a few months ago, one of you left a comment asking me to flush a piece of sodium down a toilet, which seems like a ridiculous request, but I have got Cody from Cody's lab to come out here with this infamous mercury flushing toilet so we can put that experiment to the test.
So this is the same toilet I used for my flush mercury experiment. I cleaned out all the mercury and added a spare toilet. So basically it's good use.
Now, if you take a quick look at sodium, it's a very bendy, very flexible metal.
I kind of think it's about the hardness of beeswax. Sodium metal is incredibly reactive. It only has one electron in its outer shell, and so it's actually higher on the activity series than hydrogen.
Now, most people will store sodium in a container of oil because it prevents an oxide layer from forming. I just kept mine kind of in a jar, so you can see it's got that crusty coating. But if we take a knife, we can cut this open, and for a brief second, you can see that shiny metal, but within seconds, you can see it's oxidizing, and and forms that white, scaly exterior coating. Now, sodium metal does not like to be confined. This piece is only the size, a little bit bigger than a marble, but if we throw this into the toilet and then drop a block of wood on top, it creates enough pressure and enough heat quickly, the wood will get blasted back out 10 to 20 feet in the air, no problem.
I think it like bounced around and it finally landed on top of it. It's like a good 30 feet from the flush zone.
If you feel this block of wood, it's actually really slippery, really slimy. So check this out, we rigged up this contraption. It's just a long piece of PVC pipe so we can flush the toilet from about 10 feet away. It's gonna drop this into the toilet bowl. We're gonna let it fizz around for a bit and then we're gonna flush it and see what happens. Here we go. I can hear it crackling and fizzing.
All right, flush it.
Okay, here we go. That's what you call explosive experience on the toilet. The biggest chunk of sodium I've ever thrown in the water. So a little bit nervous about this one. We're definitely flushing this in distance. And I think we actually have Cody throw it in this time. Help you the smooch. That reaction actually was pretty cool. This time we're going to do the same thing. We're going to flush it and see if we can make it go off during the flushing process. I'm wondering if we should go a little bit bigger just to take it to the next level. This is the grand finale. We've got a whole handful of sodium here, like 6 chunks. We're going to throw them in, and at that exact moment, Cody's going to flush, and hopefully we'll get some kind of a reaction. Ready for this?
Oh my goodness, that's amazing! Check that out. It's still smoking. We got fire. A little.
Good thing he's wearing
Oh my
glasses.
gosh.
Guys, this is insane.
Real gospel.
That used to be a toilet. Now it's a big mess that we need to clean up. I honestly have to say I wasn't expecting that to go off. Like when you flushed it and nothing happened, I was just sitting there thinking, okay, another fail. And then boom!
What did we do, man? That's been crazy.
So we broke a toilet. I guess that's what happens when you flush a substantial amount of sodium down it. This is not something you want to try at home. This is for demonstrational and educational purposes only. So you can see this is pretty dangerous stuff, and it is reacting with our skin right now. It's probably turning my forehead into a bar of soap, but we did this for you guys. Thanks for the request. This is a ton of fun. I've never seen a toilet explode before. Anyway, huge thanks to my friend Cody for coming down here and making this possible, for sacrificing this toilet on our behalf. Luckily, he's got a backup, and we're going to do a video on his channel flushing liquid nitrogen down the toilet. Can the ceramic withstand liquid nitrogen? We're not sure, so we're going to test that out. Go over to Cody's channel and check him out. Give him a subscribe. He's got some epic content. Thanks for joining us for this experiment. We'll see you in the next one. Talk to you then. All right, let's clean up this.
Alright, so it just gives you an idea of how reactive this stuff is. So this stuff is exceptionally stable. So as far as redox property goes, even though it's an oxidizer, we really consider it to be too weak. It's not going to be very reactive. How about chloride?
It's very reactive.
Well, chloride, let's go up. Let's find chloride. There it is. Here's chloride. Up here at the top is fluoride. So what do you know about fluoride? Fluoride is strong or fluoride is weak? Fluoride is the weakest because fluorine is the strongest. This is a conjugate relationship. So fluorine, I don't have a good video for fluorine, but I used to be a fluorine chemist one time. I used to use fluorine all the time, and I was trying to make different things. But when I got introduced, you know, the fluorine for one thing is fluorine gas cylinders are stored in a steel box. We put them in a 1/4-inch steel plate box. That way, if there's any leak, it gives you time to escape, you know, because it has to eat through the steel box first before going out into the lab. And so we had that, and then I was taught the fluorine chemist handshake when I started fluorine chemistry. Do you know the fluorine chemist handshake? The first year you go to the fluorine chemist conference, it's like, hey, how you doing? You know. And the next year you're there, it's like, hey. And then next year, and then you have to retire from fluorine chemistry altogether. Fortunately, I retired early. I still have my fingers, but I remember going to shut off one of my valves with fluorine, and then you know I wore three layers of gloves. And I go to shut off the valve, and my gloves catch on fire. It's a pretty amazing sight. And then I knew I had a leak. It was a very tiny, like pinhole leak, but still significant. And they say like fluorine can catch stainless steel on fire. I think I mentioned that before. You know, stainless steel is very hard to oxidize, you know, compared to iron or regular steel. Regular steel is pretty easy to oxidize and rust pretty easily, but stainless doesn't. But fluorine will catch the stuff on. You don't need a spark, you don't need a match, you don't need anything. It'll just catch it on fire, unless it's been passivated. I use Monel steel. Then I gently passivated the Monel steel so it wouldn't catch on fire. But the other components did catch, you know, the other components were eaten away of the valves. I had to replace the valves every week, you know, because the fluorine would just eat it up. But anyway, fluorine is extremely reactive. That means fluoride is extremely unreactive. What about chloride? Chloride is unreactive. Chloride's unreactive. Well, how unreactive is chloride? And so let's be a little bit more definitive. So chloride is what we call a reducer. It is weak. But it's not so exceptionally weak. You know, it's not in the top 5 here, down here. So chloride will react with more stuff. Well, what exactly will chloride react with? Now, when we think about redox reactions, we're thinking of a tug-of-war for electrons. And tug-of-war would be like chlorine wants electrons, chloride has them. So this chlorine is going to come and try to take electrons from chloride. So if there's a tug-of-war for electrons, chlorine versus chlorine will end up in a tie because both chlorines are going to be equal in strength. And so what we say is that chlorine will not oxidize chloride, it will result in a tie. Well, if something holds on to its electrons more tightly, like fluoride, then there's no way chlorine can oxidize fluoride, because fluoride holds on to the electrons much more tightly than chloride. In other words, fluoride is an even weaker reducer than chloride. And so if chlorine tried to oxidize fluoride, nothing would happen. If chlorine tried to oxidize oxygen in water, nothing would happen. If chlorine tried to oxidize sulfate, no. If chlorine tried to oxidize this water, no. If chlorine tried to oxidize manganese 2+, no. If chlorine tried to oxidize lead 2+, no. If chlorine tried to oxidize chloride, no. However, if chlorine tried to oxidize chromium 3, it would be successful. Why? Because chromium 3 is a stronger reducer than chloride. And so what we can say is this. If I wanted to be more specific in terms of chemical properties, I would say it's a weak reducer, yes. And so it can, chloride is a weak reducer. Oops, I went the wrong way, sorry. Let me backtrack a little bit. I'm not thinking in terms of chlorine. I don't have chlorine. I have chloride, right? And so if I have chloride, which is different than chlorine, then is chlorine capable of oxidizing chloride? No, it's going to be a tie. And so if I want to oxidize chloride, I need an oxidizing agent that's stronger than chlorine. Well, what's an oxidizing agent that's stronger than chlorine? Fluorine. And so if I had fluorine and reacted with chloride, no problem. The fluorine's going to take the electrons from chloride. So if there's a tug of war, chlorine on one side, and fluorine on the other side, who will win that tug of war for electrons? Fluorine. And so fluorine versus chloride, or fluorine versus chlorine for that extra electron, fluorine's going to win. Ozone? Ozone will win. This disulfate type ion, that will win. Hydrogen peroxide will win. Permanganate in acid, permanganate will win. Lead-4 will win. Chlorine, it'll be a tie. Dichromate, dichromate's weaker than chlorine. Will dichromate take the electrons from chloride? No. And so what we say is this. We say that chloride is a reducer, it's a weak reducer. Reacts with oxidizers stronger than chlorine. And so any oxidizer that's stronger than chlorine can take the electron from chloride. So this conjugate relationship. And so that means any of these work. Now, we're going to do one of these in lab on Thursday. We're going to use permanganate. We're going to use potassium permanganate. We're going to react it with HCl. When we take potassium permanganate and react it with HCl, then the potassium permanganate will oxidize the chloride to form chlorine gas. And so we're going to generate fresh chlorine gas in lab using permanganate. Okay, any oxidizers that are weaker than chlorine will not work. So for example, what's the weakest oxidizer? The weakest oxidizer would be lithium ions. For sure, lithium ions don't have enough power to oxidize. And so lithium ions plus chloride, no reaction, no redox reaction. Potassium ions, forget it. Calcium 2, none of these are strong enough to take electrons from chloride. None of them. And so we just keep going up the list. None of these. And then finally we hit chlorine, but chlorine versus chloride tied, and then we got to go above. And then we'll have reaction. And so here, chloride can react with powerful oxidizers. Sodium ion, likewise, we could do the exact same thing for sodium ions, because sodium ions are here. And so I said sodium ions are pretty much unreactive, but that's not accurate. Sodium ions can react. So sodium ions are an oxidizer, but they're exceptionally weak. They're at the bottom of the list here. Sodium ions, can sodium ions take electrons from sodium metal? No, that would be a tie. Sodium versus sodium is going to result in a tie. Can sodium ions take electrons from magnesium? No, magnesium is even worse of a reducer. Reducers give up electrons. So if sodium is here, magnesium is worse because lithium is here. And so sodium ions will not react with any reducers weaker than sodium, equal to or weaker than sodium. So there's no way it can take electrons from any of these species, especially fluoride up at the top here, fluoride being the worst. However, sodium ions can take electrons from calcium. Sodium ions can take electrons from potassium and lithium. So when I said it doesn't really react, that's too weak to really be considered, well, it does react with a few species, but these species aren't more rare, kind of exotic species, so we really don't consider it. You know, so if you took table salt and mixed it with lithium, not a good idea. Ew. Okay. So, That's the chemical properties of sodium chloride. Now, let's do is see what you guys come up with here. Can you come up with the chemical properties of another sodium solvent? We're going to try sodium nitrate. Okay, tell me the chemical properties of sodium nitrate, but can you do it on this card? I want to see what people are thinking. This chemical property. Tell me the chemical properties of sodium nitrate. All right, after you get it done, are you done with it or still working? Still working. Okay. After you are finished with that, you can go on a break.